This is an example of setting up a differential equation from a statement of a problem. And so this is something we'll be doing quite a bit over the course of the semester. In this case, this is a standard mixing problem that you may have seen in calculus before. There's a little bit of a twist here that makes it different from the version you would have seen in calculus. So when we're trying to model with a differential equation, the two questions we should ask are, in this situation, what quantities are actually changing? And then secondly, how are the changing quantities related to each other? So this is always where we'll start. In this case, there are a few things changing. The actual volume of water in the tank is changing. The volume of, I should say, liquid in the tank, because it'll be a saltwater solution. Over time, the concentration of the solution is changing. Because you're pumping the mixed water out and pumping pure water in, so the saltiness of the water is changing. And then just the quantity of salt. So the kilograms of salt are changing. And this question is trying to be helpful by telling you to let the variable y represent the number of kilograms of salt after t minutes. So that's telling you that that's the one you should focus on, but all of these things are changing. The relationship between these is that the quantity of salt is going to be the concentration of salt in the water times the volume of the liquid. So this is going to be like an algebraic relationship between the three things that are changing. And so that makes sense that if you understand how two of these are changing, then you can figure out the third from this equation. Okay, so now we're going to try to understand the rates of change of these different quantities. In this particular problem, I don't have to really think about rate of change of the volume of the tank because it's a linear change. In other words, I can just say what a formula for the volume of the tank is, because I have pure water coming in at one rate and then the mixture is leaving at another rate. And so I can see the difference between these two is 3 liters per minute. So the water is leaving 3 liters per minute faster than it's coming in. And I know the initial amount is 2,000. So I can actually write down a formula here that describes volume of the tank. I could just say it's 2,000 liters minus 3 liters for every minute. And I am told there that T is measured in minutes. So this will be the actual volume of tank volume in the tank. It's possible that that's not that easy to see, and then I would have to look for information to try to build that up from the rate of change of volume. But in this case, I think I'm pretty sure about this as a formula for the volume after T minutes. And I didn't write it down here, but our initial value is 70. They tell us that at the beginning of the process, there's 70 kilograms of water. And so I could also figure out the initial the initial concentration. It would be 70 kilograms per 2,000 liters would be the initial concentration of the tank. So I'll just make a note of that. So initially 70 kilograms per 2,000 liters. And I only point that out because sometimes it's easier to think about some of these quantities with specific numbers before you try to write down an algebraic formula for it. And of course, that's not a formula for the concentration, that's just an observation about how it starts, but it allows me to do the calculation once with numbers. And then the kilograms of salt is the variable y in the problem. All right, so now I'm ready to take this relationship I have at the bottom and try to turn it into some kind of formula.